All right. Good morning. My name is Kyle Kraft,
My name is Grant Hecht.
and we're from Missouri University of Science and Technology and presenting the initial development and verification of a precise orbit determination filter for the Apex CubeSat mission. As a quick overview, we're going to start with an introduction to the mission, then break down the estimation architecture, and then we're going to verify that architecture using STK and ISAT data and end with some conclusions. So as an overview for the APEX mission, or the Advanced Propulsion Experiment mission, we're a 6U CubeSat funded through the Air Force Research Laboratory's University NanoSat program NS10 competition. And the goal of the mission is to test a multi-mode ionic monopropellant electrospray, or MIME thruster. Now this thruster is unique because it has two propulsive modes. It has a higher thrust, lower ISP catalytic chemical mode, and a lower thrust, higher ISP electrospray mode, which we'll call chemical mode and electric mode for the rest of this presentation. And what makes it so versatile is that you can choose between these two propulsive modes with the same propellant and propellant feed system. So you don't have to change systems, but you can change propulsion types. And the goal of this study and the mission overall is to develop a means to accurately determine that thrust using the sensors and assets available for CubeSats. Now, some of the driving requirements for full mission success is that we're going to need to determine the performance characteristics for both chemical and electric mode to within a 10% error range. Now, this was given to us by our partners in the endeavor, Froberg Aerospace, the individuals developing the thruster. And the primary performance characteristic that they're looking for is the average thrust magnitude throughout the course of the maneuver. Now, the error range, that 10% error range, is defined as 10% of the estimate itself and the one standard deviation value. So if we have a 100 Newton thruster, we want our one standard deviation of our estimate to be 10 Newtons. To do this, we've isolated two different maneuver types, an orbit changing maneuver and an attitude changing maneuver.
Although an attitude change maneuver originally seemed more enticing due to the ability to easily back out thrust from gyroscope attitude rate measurements, an orbit change maneuver was chosen due to the potentially risky high attitude rates that could be achieved, particularly in chemical mode, that could damage critical components and increase difficulty of successfully downlinking data. Thus, an orbit change maneuver was ultimately the more practical choice, although it does pose an increased difficulty in accurately estimating the thrust.
So to start, let's have an overview of what stochastic orbit determination is to make sure that everybody's speaking the same language. So it differs from a deterministic approach because your answer also has an uncertainty coupled with it. So we're going to start, or to start statistic orbit determination, you'll usually have some form of a state space approach where you have a state vector being estimated, usually represented by a lowercase x, and some uncertainty in that state represented by a covariance matrix, again, usually a capital P. Now, the figure on the right does a really good job of explaining the basics of stochastic orbit determination, where you have some true trajectory and some true position at true times represented in black, and then you're going to have some uncertainty in your timestamp and your measurement, which results in some estimate shown as an X. And what you want is that estimate uncertainty that comes with your stochastic OD to encompass the actual true trajectory. Moreover, because we're looking at such low thrusts in the electric mode, there's no real-time way to accomplish this. So the best post-processing way to do it is to use a batch filter. Now, a general batch filter is a least squares linear estimator that you apply iteratively to a nonlinear problem. So the figure down here does a pretty good job of showing this. You start with some initial state guess, which has a maneuver value in it, so some thrust value in it, and your first iteration is going to be incorrect. And you apply that linear least squares correction to your initial guess, and then you get closer and closer. And as you iterate this process, you converge to the actual trajectory of your satellite, and that's the estimate that you use.
The thrust determination filter estimates the dynamic states at an initial epoch, as well as drag and solar radiation pressure coefficients, measurement clock biases, and thrust, while considering uncertainty in the attitude and mass of the satellite. The filter's dynamic model, which is used to propagate the state and linear state transition matrix, includes a 72 by 72 spherical harmonic gravity model using EGM 2008 gravity coefficients, as well as spherical drag and solar radiation pressure models employing an exponential density and co-rotating atmospheric model, and constant solar radiation pressure. The spacecraft's attitude is used to compute the relative surface area for both drag and solar radiation pressure induced accelerations. Third body solar and lunar perturbations are also included. The filter determines the thrust by iteratively computing the linear correction to the initial reference state from accumulated information using the least squares approach, which attempts to minimize the measurement residuals. This iterative process continues until the thrust estimate converges. The thrust determination filter relies on both internal and external measurement processing. The internal measurements, which are used during the propagation and accumulation of information, that are not included in the process batch measurements. These include measurements of the GNSS receiver clock, attitude quaternion, and the spacecraft mass. The external measurements are L1 and L2 pseudoranges, which are combined to correct for over 99% of the ionospheric effect. Expected pseudorange measurements are generated by interpolating GPS satellite parameters provided by published International GNSS Service final data products. As shown in the table, the final data products provide GPS satellite orbit solutions with an accuracy of about 2.5 centimeters and GPS clock states with an accuracy of about 20 picoseconds, all at 15-minute intervals.
To test the robustness of our filter, we'll need to use an external dynamics model to generate our true trajectory. We chose AGI Systems Toolkit and specifically their high precision orbit propagator to do this. The next thing we'll want to test is the statistical consistency of our filter. To do this, we conducted a 1,000 trial Monte Carlo analysis and examined the realized uncertainty that our filter determines and compared that to the true error distribution or the true uncertainty in our state. Now below, we'll see the initial parameters for our STK verification, which aligns with the ISAT verification method. So you'll see that we're in a polar orbit with an approximate altitude of 600 kilometers. Next, the only maneuver that we considered for this study was our electric mode maneuver, which has a nominal thrust of 33 micronewtons. This serves as a very good benchmark moving forward because it's 3 orders of magnitude lower than our chemical mode thrust. The maneuver duration was 1,500 seconds, and it was in the angular momentum direction, and we had an hour and a half of drift time collecting pseudoranges in 30-second intervals before and after that maneuver was conducted. You'll see the measurement statistics shown here for how we corrupt via noise and biases in our measurement models, and the attitude was held constant to make sure that the Monte Carlo was tractable. Lastly, our initial guess was corrupted from truth randomly, so we had a Gaussian distribution, again with the statistics shown in the table on the right. Now here are the results for our position and velocity states, where we have the x-axis representing mission elapsed time in hours, and our y-axis represents our actual state errors, where we have position in meters and velocity in millimeters per second. Now, one thing I want to point out immediately with these graphs is that the red line represents the single trial error, so a single Monte Carlo trial, what its error was. And the black line represents the plus and minus 3 standard deviation or 3 sigma confidence interval from that filter trial. So what we're looking at here is one filter's realization of uncertainty and the actual error that encapsulated it. The dashed gray line represents our true uncertainty, so our true error distribution for all 1,000 Monte Carlo trials. So you look for 2 things when you examine a graph like this. The first is you want this red error line from a single trial to stay within your 3 sigma confidence interval realized by the filter, which we see for the vast majority of the trajectory for all 3 states. Next, you want to look at the statistical consistency, which is represented by how well the solid black line aligns with the dashed black line. So we'll see that the 2 lines are within centimeter and in most cases millimeter level accuracy of each other. So because of this, we can say that the filter is statistically consistent. And moreover, we can prove that our filter actually provides position realizations of centimeter level accuracy. The velocity is shown in the graphs to the right, and we'll see that we have millimeter per second level precision in all of our velocity channels. But most importantly is our thrust estimate. And I'll remind you that we need to determine our thrust within that 10% error range, which for electric mode is 3.3 micronewtons. Now we put the restriction on ourselves to have 3.3 micronewtons be the 1 sigma level. But if you look at the error histogram where the thrust errors are shown in micronewtons on the right here, what we actually see is that our 3 sigma confidence interval, these vertical dashed black lines, is well below that 1 sigma threshold. In fact, if you add the bias represented by differences in our dynamics and the 3 sigma confidence interval, our entire error distribution is below that 3.3 micronewton threshold. And moreover, we see that the distribution shown in our errors is accurate to what our filter realizes the 3 sigma confidence interval is. So we say that our thrust estimate is consistent and accurate to meet the mission requirements.
The Ice Clouds and Land Elevation Satellite, or ISAT, launched in 2003 to a low Earth orbit and had the primary mission objective of providing geological and climate data. Published data from the ISAT mission is publicly available and includes precision orbit and attitude determination solutions, as well as raw GPS pseudorange measurements, and was thus chosen as the primary candidate for verification of the thrust determination filter using real mission data. Verification of the filter using ISAT data allows for further assessment of the filter's robustness when subject to true flight dynamics attitude measurements, and real L1 and L2 pseudorange measurements. To assess the filter's performance with ISAT data, a batch of GPS pseudorange measurements, which were corrected for ionospheric effects, was generated from the published raw pseudorange data. Attitude measurements, which are used during the propagation and accumulation of information, were provided by the published precision attitude determination data. The published geometrical properties of the spacecraft were used to compute relative surface areas for the dynamics, as well as the location of the GNSS receiver in the ISAT body frame. No active thrusting was performed during the period evaluated, and thus the true thrust magnitude is 0. The thrust direction was defined to be approximately perpendicular to the velocity direction, which aligns with the STK verification. Proper filter performance will therefore result in a thrust estimate that converges to 0. The precision orbit determination data is taken as near truth and is used to generate a corrupted initial state guess. This data is also used to compute approximate position and velocity estimation errors. Due to the 0 thrust magnitude, any non-null thrust estimate is taken as thrust estimation error. This table here provides the estimation errors for position, velocity, and thrust for our initial ISAT verification trial. As you can see, the dynamic states were estimated with reasonable accuracy for the first iteration, and the thrust over a 3,000 second evaluation arc was determined with millinewton level accuracy. The ISAT satellite at the EPICS process had a mass of 882 kilograms. Thus, this determined thrust represents a 12.5 micronewton level error if the equivalent acceleration is applied to a 10 kilogram CubeSat, such as Apex. The estimation errors observed are likely due to GPS signal propagation delays due to the ionosphere and effects neglected within the filter's dynamics model, and are expected to be greatly mitigated with the reduced dynamical complexity for a cube satellite form factor, as well as with improved ionospheric modeling. Therefore, although current estimation errors lie outside of the desired accuracy, sub-meter position error and sub-micronewton thrust error is expected in the final filter design. In conclusion, an improved consider batch filter was developed that is capable of precise thrust and position determination by processing dual frequency GPS pseudoranges and star tracker attitude measurements using commonly available cube satellite sensors. This presented consider batch filter is also easily extendable to other small satellite form factors for estimation of dynamic states and parameter estimation. Future work will include improved ionospheric modeling for our predicted pseudorange model and a revised ISAT verification to align with the APEX mission requirements.
And we'd like to thank Missouri S&T, MSAT, Froberg Aerospace, Dr. Jacob Darling, the FRL Summer Scholar Program, and UMP for making this mission possible. Thank you.
Okay, gentlemen, thank you very much for the presentation. A couple of questions from the judges. First one is, what measurement frequency is required of the GPS and star tracker devices to meet the required positional accuracy requirements?
Yeah, so we haven't done the full error budget on that, but what we've seen with previous studies is that we can get away with pseudo ranges between once every 30 and 60 seconds because we can process those accurately, and we've got a long enough arc that we can get away with that. The attitude is more a function of what type of attitude rates we want to put on the satellite. So right now with the ISAT mission, we had it 1 hertz, but we can interpolate the attitude quaternion. So I think with the analysis that we've done, we're pretty confident once every 30 seconds and 1 hertz is going to be able to meet our mission requirement.
Okay. Have you evaluated the sensitivity of positional accuracy to delays in the star tracker solution? So if you had dropouts or occlusions?
We have not. So we could incorporate some kind of correction as we did with the GPS pseudoranges, where we correct those time biases on our GPS measurement timestamps. That could be a possibility that we could look into, but currently we're not looking into correcting anything from the star tracker as far as the timestamps go.
Yeah, we just consider the uncertainty, and we assume that the satellite will not have angular rates that are that high, because that would be kind of detrimental to the mission as well.
Mm-hmm.
Okay. Let's see, is the proposed filtering method sensitive to thermoelastic distortion of structure and/or resulting changes in alignment of the star tracker, satellite reference points, etc.?
So we're not for the elasticity of the structure, but we do in the consider parameter for the attitude state we include the biases from misalignment and thrust vector misalignment for this. So for the star tracker and for thrust vector misalignment.
Okay. Let's see. Can you talked just a little bit at the end about your future work efforts, and can you expound a little bit on the true time transmission of GPS, improved position accuracy, thrust determination, et cetera?
Yeah, so one of our proposed ideas for the biggest contributor of error is the delay due to the ionosphere. So we can actually correct for that delay in the actual pseudo-range measurements, but as far as computing the time of transmission from the GPS satellites, improved ionospheric measure or modeling should be able to improve that calculation so we can get a better idea of the expected time that the signal was transmitted.
Okay. Thank you very much for your presentations, and looking forward to future discussions. This concludes the presentation, and I will at this point turn it back over